Well, hello and welcome to Genomics in the Cloud Book Club, Week 13. I'm your host, KT Picard. In today's meeting, we'll be talking about Jupyter and analyzing data interactively. It really is the summit of the book and brings together all the principles that we've been working on over the past few meetings. We'll be bringing in additional resources and, of course, our usual open discussion. This week, it is my pleasure to introduce our sixth guest speaker. We round out our experience working in the cloud now by interacting directly with data. Today, we're honored to have someone who teaches coursework incorporating today's topic, the Jupyter Notebook. He is currently a consulting manager in life sciences at NFOT in Cambridge, UK. Previously, he was a researcher in applied math in the US and the UK. He has a PhD in mathematics from Ghent University in Belgium. While in Belgium, our speaker knew Geraldine and had an inkling that she was going to do great things, and I could not agree more. He's been a regular contributor and he has a keen eye, most recently solving a vexing smart dash problem before one of our meetings to keep us on schedule. Please welcome Dr. Joris Vankerschiver.
Thanks for the wonderful introduction. I'm really glad to present this material. I'll try to stick to the schedule so that we have a little bit of time afterwards, but feel free to interrupt me if I'm going overboard. Right off the top, I have to say this was a very fun chapter to work through because in my experience, usually if you have notebooks from elsewhere and you work through them, something always breaks. Like maybe a package was updated to a new version, or there's a slightly different construct, and then you have to hit Stack Overflow. And that wasn't the case here. I was impressed to see everything run through, running all the commands. So yeah, it was both an interesting and a good experience. So what I would like to do for today is slide-wise, just go over the infrastructure and how the notebook works and interacts, especially with the Terra environment, and then go back to the notebook that we all worked through as part of the reading for chapter 12, and maybe present a few extra resources if there's time. So in a nutshell, the notebook, as it's shown on the slide, it's basically something that runs in your browser. And you have cells where you can type Python commands, originally at least. You execute them with Shift-Enter, and then you get the result right back. And the good thing about notebooks is that they allow you to interactively explore, so try things out and basically see if you can get somewhere. And they also provide you with a way of keeping that analysis and reproducing at the later stage. So unlike doing things on the REPL, where the moment you close your terminal, it's gone. The notebook gives you a record that you can build on or even share with other people. Could you go to the next slide, please? And so when we talk about the notebook itself, there's like that's the top of the iceberg. So a Jupyter notebook is a document, and in Terra, the notebooks are stored in a bucket on Google Cloud Storage that you have available. But then the question is like, okay, how do you run the instructions? How do you run the code that runs that is inside your notebook? And for that, you have this notebook runtime environment as part of Terra that consists of a number of moving pieces. And the way that comes up is basically, well, you have to make a judgment call about what you need in terms of resources. And the default environment sort of gives you a moderate amount of resources. I think it's 4 CPUs and 15 gigabytes of RAM, but you can customize that and either have more resources or even command a Spark cluster if you want to do heavy-duty data analysis. So that's sort of the hardware, the metal. And then in front of that sits a Docker container of the kind that we've seen, with probably a bit more trimmings than what we've run so far. But in that Docker container, you have a Jupyter server running. And what that does is it basically takes the commands that you send it every time that you do Shift-Enter. It executes those commands and then sends you back the output. And the container itself is also customizable because it's not enough to just have a Jupyter server. There's also a lot of moving pieces and dependencies that you can configure there. So for instance, if you choose the default container that's available, you get GITK, you get a certain version of Python and some standard data analysis packages. But if you need more or different packages, then that's something that you need to configure. And that brings us to something that was described quite well in the book. If you want to configure your Docker container, you can do so, or at least configure what runs inside it. You can do so via a startup script. And I think that's on the next slide. So here we have systematically how that works. So the startup script is basically a bash script that whenever your Docker container is set up, gets executed and allows you to customize it. And I don't know if on the next slide or so we have a little bit more about the startup script, but if not, then I can show it later on. I think, oh yeah, we have. So here we have a little bit more about the collaborative mode. So Jupyter notebooks are decent for collaborating with other researchers, so especially for results sharing, which is their prime reason for being there. Terra gives you capabilities to edit things in tandem. As the book points out, it's not a fully fledged asynchronous collaboration mode like Google Docs would offer you. But you can open a notebook that someone else is editing and at least look at it and run it in playground mode so that you have at least that modicum of sharing. And so with that, maybe I think we should switch to, I can walk through the environment and talk about the various commands to run, and then we can come back to the presentation at the end of it, if that's okay. Thanks. I will share my screen. Okay, can you see my screen?
Looks great.
Sorry, I'm just moving all the Zoom windows out of the way. So here I'm in my Terra workspace that I made last week for the investigations that we did then. And just before the meeting started, I started my cloud environment by means of, there was a little triangle here, so click to start running. It's still running and it's telling me that it's consuming 20 cents per hour. So maybe just to follow up a bit on what we have available here, if you click on the gears, so there's all sorts of configuration that you can play with. You can choose from different environments, different Docker images that are pre-configured. You can even, if you go digging, provide your own Docker image. And then you can also configure the amount of resources that your environment has. So as I mentioned, 4 CPUs and 15 gigs of memory. And here I supplied the startup script that came with the book. I left the compute type as standard VM because I don't want to run a Spark cluster for now. And then given that my machine is already up and running with that configuration, the update option here is grayed out. But if I change anything here, it would allow me to update my cloud environment to match what I wanted. And so, for instance, one thing that I did when I walked through the notebook over the weekend was I forgot to supply the startup script, and then all sorts of things didn't work for me. So I had to go back and enter that, and then Terra basically rebuilt the environment for me. Took a few minutes of work and then dropped me right into it. So even though there's a lot of moving pieces below the surface, like that's nicely abstracted away if you're an end user. So given that it's already running, I'll close that again and go to the notebooks section here. And when we cloned that workspace, we all had two notebooks, Genomics notebook and Genomics notebook executed with the output already provided. What I did was I made a copy of Genomics notebook before I got started so that I could mess around with the notebook to my heart's content and not have to reclone or restore it from a prior state. So we'll open that. And by default, we get a preview of the notebook. And if I want to edit it, I can go to edit. What that does is it copies the notebook from my bucket into my running cloud environment and basically drops me right into it so that I can start playing around with the notebook. So maybe just to get started, so there's a couple of large pieces here. So there's a little bit of information about running Python code from within Jupyter. And actually, let me make this font a bit bigger. There we go. And then there's a couple of genomics related workflows and tutorials. So one is about visualizing genomic data in IGV from within the notebook. And then there's a workflow about running GITC. And finally, visualizing basically data that you've created with GITC. And that points a little bit to the reason for the notebook existing in the first place and being useful in this context, because we've all typed in the commands in our VM and we were able to run things like that. And then we copied files into buckets and visualized them. So we know how to do all of this stuff, but the notebook provides a convenient way of pulling it all together, doing everything from one and the same environment. And it also allows you to immediately interact with sort of interactive compute. So if you run GITC and you have your variant calls and you want to do some data analysis on that, that's only an R or an import Python, import pandas or whatever away. So it is very convenient, and the interactivity also means that it's easy to tweak commands, which is good for exploration, or if you want to debug something and you just want to run things in a tight loop a couple of times and see where the problem is. So with that, I think we can spend a little bit of time going over the cells in the notebook. So I will go into cell and then delete the outputs. All outputs clear, so that we can see how things appear little by little. So I should say you have all of this text here, these titles. You can edit those before we do any Python. So everything that you see in the notebook is editable. This is markdown text that you could easily add to make it more explanatory. But let's stick to the Python. So the way that we execute the code in a cell is by hitting Shift-Enter. So here we have another markdown cell that I just executed. And now I'm on this first cell right here that says print hello world. And if I do Shift-Enter, that gets executed and the output dumped into my notebook. And I can do that a couple of times. There's some various constructs, introducing new variables and then doing the same thing. But you basically see how that works. And then the nice thing about the notebook is that it's not specific to Python itself. So the book points out that Jupyter, which is the environment that we're using, the name is on the top left here, is an amalgamation from the first letters of Julia language, Python, and then R, with some interpretation. And basically, the way that came about is that people built this interactive environment in the browser to run Python code. And then they realized that, hey, there's actually nothing special about the Python interpreter sitting in the background. So all I have is something in the browser that takes commands and executes them somehow, and then it gives me back the result. But I could swap out the Python interpreter by an R interpreter, say, or by a Julia interpreter, and that would work just as well. So that's a bit like the philosophy behind Jupyter. What we do here is related. So we run actually a separate package that was installed as part of our runtime, rpy2. And then we also get some extensions to make it easy to interact with that package from within the notebook. And so what this loadext rpy2.ipython gives us is basically this %r magic command. And anything that you put after %r, so you can put valid R commands there, as the name suggests. And if you run those cells, that command then gets sent to the R interpreter, executed there, and pushed back, the output pushed back into the notebook. So here we print hello world again, and we see the output coming from R. And just a very subtle detail, but maybe you're wondering, like, what is this array hello world D type U12 mumbo jumbo? That's actually quite interesting in the sense that the print statement in R doesn't just print something, but it also gives you a return value. And you see that here, that one hello world. And what rpy2 does is basically takes the outputs of anything that happens in R land and then tries to give it back to Python. So here it takes that hello world string, wraps it in a NumPy array, a Python array, and then gives it back. So it's a little bit overkill here, but you can also imagine moving complex data structures into Python, into R, and then conversely getting them back and sort of mixing and matching and getting the best of both worlds. The next command up, %r, is pretty much the same thing, except when you have a magic command that has 2 percentages, it applies to the entire cell. The single percentage is just the command that follows it, and 2 is everything in the cell. Another thing that the notebook does, and actually before I go there, I just want to make a small detour and check the clock. So if you do data analysis, Python is the language of choice, at least in notebook environments, with R also playing a very big role. But there's basically no limitation to what languages these days you can run in notebooks. So if you're a Julia aficionado or any other interpreted language, then you will find something in the notebook that you can use. And in particular, one thing that I found quite interesting that came up a couple of years ago is that people were sort of smart enough or brave enough, I don't know what the word is, to get C++ to run in Jupyter Notebook. So they sort of found a way to link up the C++ compiler so that if you typed in small snippets of C++ code, that you could sort of evaluate them on the fly and get the result back. So I don't have anything to show here, but if you've written C++, you will be familiar with this. And this is just an example to show you that a Jupyter Notebook is really widespread these days. So back to the notebook that was provided. Another very powerful construct is if you precede a command with an exclamation mark, then whatever follows that command is interpreted as a shell command. So that gets run then on the shell of the underlying operating system that you have in your container. So here what we can do is, for instance, run the Unix command echo hello world. And that does, again, the same thing as the Python version and the R version. It prints hello world, but it does that from within the shell on your machine. One thing that's important to keep in mind is that the notebook really runs in the cloud, in a Docker container somewhere in a data center. It does not run on your browser per se, or let alone on your machine. And so if you have Unix in your fingers, you can sort of try to test out the limits of your world, so to speak. So I added a few more commands here just to showcase that, hey, yeah, we're not in Kansas anymore. We're really in an environment somewhere in the cloud. So for instance, the Unix host name command tells you the host name of where you run. And that's some bizarre auto-generated name, presumably of the Docker container somewhere on the Terra backend. And then some more Unix commands to show that we're running Linux over there. And even like going really close to the metal, this shows you that we are actually physically inside a Docker container. So that was going down the weeds a little bit. I will skip over that and continue with the rest of the notebook. One thing that the exclamation mark gives you is a very convenient way to interact with GSUtil. So the Google Cloud command line utilities are installed in your container. So they're available from within your notebook, and we can use them to interact with data in the cloud. So what we do here is we first list the contents of the Genomics in the Cloud bucket. And then we copy a file out of it, hello.txt. And that takes a little bit of time, but then when it completes, what that means is now we have a file, hello.txt, in our local environment where the notebook is running, and we can even have a look inside that file, and it says, hello, dear reader. And by the way, I should move this and have a bit more vertical space. So moving on from that, we're going to access data from the bucket a couple of times. So we'll make that easy for ourselves and create a Python variable with the location of the bucket and the data in it so that we don't have to type that in. And now we'll get some data out of it. So first we list the contents of that folder again, and then we move on to get some of the BAM files out of that. So here we have the BAM files that we analyzed in chapter 5, and we copy the BAM file and the index for the mother to our local storage. And if we then do an ls again, so for list contents, then we see that we have in our local environment the mother.bam and mother.bai file, as well as various other files. So this is good if we want to grab data from Google Cloud and bring it over to analyze it in our cloud environment. We can also do the opposite. If we run GITK, chances are that we're going to create some interesting outputs that we want to save somewhere. Because it's important to realize that when your cloud environment goes away, that basically takes away your storage as well. And especially if you want to share or persist or make available, then you probably want to copy your data somewhere that is easily accessible. So here we do the opposite of what happened before. We make a directory, we copy the files into it, double check that the files are there. Actually, I have a bit more there because I already ran the analysis. So let me actually remove that data. So I will do something dangerous. I hope I will not regret it. I remove that directory and make it again. I should have a clean slate. And I think that might have been not the wisest thing to do. Let me have a quick ls. Okay. I will copy the files back over. Okay. And this. Okay, I will not do that anymore. I'll make my sandbox again and move the files in there. And now if I ls it again, I have both of those files and nothing else. I am also going to create a variable that points to the workspace bucket that I have associated to my workspace. So that is saved or provided by the Terra environment as an environment variable. And I can grab that and actually also utilities to cells, print it out like so. So it's completely auto-generated bucket that we can copy things into. Likewise, there's probably already going to be some things in my workspace bucket because I already ran this analysis once before. Actually, there's quite a lot. It's taking a bit longer than expected, but it finishes eventually. And just to go through the steps, I'll copy that data over with the gsutil command, as we did on the command line. And then I will stop. I will not ls the data again because it's already there. So with that, that's basically using gsutil to move data back and forth. The next step up is now we have some interesting data. We want to look at it. And we're going to do that with the JavaScript version of IGV. The standalone version of which we've already used in chapter 5. We downloaded the Java version, ran it on our local machines to look at variant calls. So functionally, that's the same thing. The difference is that here we have something that runs in the browser, so we don't need to leave our convenient environment to get at that data. So we import the IGV package for this. And IGV is a Python package that is not standard, but it was installed as part of that startup script that we ran when we specified what kind of cloud environment we wanted. And then once we have the IGV package available, we can use it. So here in the next cell, we say, okay, create a genome browser. That's the igv.browser constructor. And we say, well, as a reference genome, take GH19 and take this particular locus of chromosome 20. So if I run that, that creates an IGV browser. Doesn't give me much to look at yet until I do igvexplore.show. And that takes a little bit of time to load in, but eventually I get a quite familiar looking version of IGV with the reference genome and some genes indicated. And to a greater or lesser extent, you have most of the functionality that the desktop version also provides. So you can zoom out and zoom in, and you can configure the different properties of the tracks, and then later on also the reads. And you can click around basically to your heart's extent to get more information about what we have available. So that's basically our background. Now we're going to add some data from the BAM files that we just uploaded, some tracks. And for that, we're going to call the load track function a couple of times. So here, it's a bit hard to see, but I executed cell 41 here, which loads in some whole genome sequencing data from the mother.bam file that just uploaded. And that then basically updated the view of the genome browser that we had running earlier. So you see these tracks added here, and again, you can interact with them as you wish. We do the same thing with some exome data that was provided. That's the cell 42 here. And that also shows up in the same genome browser that we had running before. And you can clearly see the difference between the whole genome sequencing data, the mountain range on the horizon, as the book calls it, and then the exome sequencing data, the volcanic islands, as they call it. I thought that was a nice metaphor. So now we're looking at data. This is already quite cool because you don't have to download that Java program and then figure out how to run it and point it to your data. So now we're going to actually generate some data and look at that in turn. But before we do that, there's one more detail to cover, and that's what if you want to view private data? So here we basically, and I think I might have misspoken, so let me go back to the germ data variable that I had somewhere up here. Right, so the germ data variable points to data from the Genomics in the Cloud bucket, which is publicly accessible, free of charge. So we were able to just go in there and grab data from it. But that's not always the case. Chances are it's typically not the case if you have some patient data or specific data for research. It's going to be in a private bucket and you need some credentials to access it. And that's where access tokens come in. So here what we do is we ask the gcloud command utility to generate an access token and store it in the file token.txt. So I'm going to ask it to do that. And an access token is basically a little secret that you can pass along with your request when you want to access some data. And Google Cloud can take that secret, validate that it's actually coming from you, and then give you access to the data if the validation checks out, or deny when the token is not valid. And as such, a token is the same as having a username and a password. So you want to keep the token secure. You do not want to print it out or even worse, upload it to a publicly available bucket. But the good thing is that tokens also have a limited lifespan. So unlike username and password, where if they get out into the open, it's basically game over, tokens are a little bit more restricted. So here in the notebook also points that out a little bit in the sense that they say, yeah, okay, we saved the token to a file, which is typically not great. But keep in mind that that file is in your notebook's local storage, which cannot be accessed by others. Then moving on from that, we read in that token into a Python variable. And then here again, you have to be a bit careful. You do not want to print out that token by mistake and then share the notebook with somebody else, because then they can potentially access your private data. But let's hope I don't do that. And then what we do here is we grab data this time from our private buckets, and we pass in the token to validate our access request. When we do that, we basically, that cell runs, and basically it loads in another copy of the whole genome sequencing data that we already had uploaded. And you can see here it's labeled as workspace bucket copy of whole genome sequencing data. So that's enough data shuffling. So now we're getting to the meat of the chapter, which is basically running GITK commands to learn, test, or troubleshoot. And this is where the power of the notebook really shines, because all of those commands that we typed in chapter 5, we can now run, and they've even been provided nicely as part of the notebook. So here we run a simple command, just running the haplotype caller on the data provided from the mother file. And one additional twist is that we're not downloading the files and then running GITK on them. We're running GITK directly on the data located in Google Cloud Storage. So the haplotype caller is smart enough to only stream what it needs and basically, avoid shuffling too much data back and forth. So we do that, and that's going to take a couple of seconds, minutes. But in the meantime, we can keep looking at the output. So we see exactly the same output as what we had in chapter 5, except that now it appears within the notebook. I personally like very much having this aspect of command line utilities running in the notebook and dumping all of their output, because if something goes wrong, you can easily save the notebook and then send it to someone else to have a look. And I find this also very, very useful for diagnostic purposes. And if you dig a little bit on the internet, there was a blog post a couple of months ago about Netflix, about how they ran a lot of their data management using Jupyter notebooks. And what they had done is the notebooks are very primitive. They just run some commands automatically. And when the commands fail, someone gets notified, and then they can grab that notebook that failed and look at the output right there and then, and presumably fix it or diagnose it somewhat further. So it's not not limited to just individuals running things. In the meantime, the command has completed, and we can double check our sandbox, and yeah, we see our VCF files appearing right there. Now that we've created our variant calls, we can load them into IGV. So we're going to create a new IGV browser with the same reference genome as before. And now we're going to load the variant calls as we did with the load track function. So execute that. And one thing that I want to point out is you have this curious prefix files here, and the book also points that out. And I didn't really understand what that was about, but IGV has somewhat of a quirk in the sense that if you wanted to look at files that are locally on your drive, you have to put a files in front of the path. So this is not part of the path, but it's just to indicate to IGV that that is a local file rather than something that's remote. And so we're also going to run add the BAM file to that. And then there we go. We have essentially the same data as from chapter 5 with that variant call and different reads aligned to the genome. So now the next step up is troubleshooting a questionable variant call. So we have that same problem as what we diagnosed in chapter 5, where you see some misalignments and you sort of wonder like, hey, what's going on there? Can we take a closer look? And the answer is yes. So in order to troubleshoot, we generate a BAM-out file with what the haplotype caller thought when it was aligning things. That again takes a little bit of time. There we go. And now we load that in. And we have to scroll back up to see basically what the BAM-out produced for us. But yeah, here we basically see haplotypes caller's view on the world when it was aligning things. And we can use that to troubleshoot our variant call. I'll go back down. And then the last part, maybe a bit quicker, that I want to go over is now that we've generated data, we want to look at it and don't necessarily always want to look at things in IGV. Maybe want to do some exploratory data analysis on our stuff. So what we can do for that is, we're in the notebook, so we'll use some R to visualize various signals of choice. And the first thing that we do here in cell number 40 is called a variance to table command. We input our VCF file, and then we basically tell it to create a table with the annotations that we're interested in. And so there are libraries to read in VCF files directly, but as the book points out, since this is a horrible file format, or at least a very complex one, you want to leave the heavy lifting to the tools that are designed for it. And here, if we end up with something that's a nice tab-separated table, that's going to make our life easier for data science. So that has run, and now we take a quick look inside that table. So we can do that again with the cat command, the command line. And here I'll materialize the table. So we printed the 300 first lines, and we see that we have the annotations that were provided on the command line when we ran the command. So that's the fields here that were provided, and as well as here. So now that we have our nice tab separated file, we can actually do some data analysis. Okay, scroll. I will first run this cell, and I will quickly add a few more cells. So here what we do is we again have a cell that's preceded with a %% magic, which means that the rest is going to be R code. So we grab the reader library and read in this file that we just generated, and basically build a data frame out of it. And just for comparison, I couldn't resist, because I'm more at home in Python. I listed the same command here that you would need to run within the pandas library to read that data in. So here we do import pandas as pd, pd.readcsv, the same file name, and we see that's tab separated. And then just to show you what that looks like in Python, again, if we look at the first 5 rows of that, we get essentially the same data, but read into a nice data frame. So the book uses R, so I'm going to stick with R from now on, except for one place, but you could remake these figures in Python if you wanted to do that. Now, we want to do some actual plotting. So we grab a helper script that was helpfully provided by the authors, and that is also available in the bucket, and we source it. So that downloads it and makes it available to our R environment. And as you can see, there's a lot of logging output here that's in ominous reds, but you can ignore that. The upshot is basically that we have some new plot functions that we can use to plot the variant call data that we've loaded in. So again, there's a couple of cells here that I will skip over. Those were Python experiments. I'll come back to those after running the R cells first. So this is part of the book. We make a density plot of the quality scores, and we basically regenerate the same figure as we had in chapter 5. And then we can also zoom in on that plot by limiting the maximum value of X, the qual score, to be 10,000. And we get this appearance. And then last, we can make a density plot where the qualities are separated by call sets, number of call sets. And just one small detail. If you like I mentioned, if you want to regenerate these figures in Python, you can do so. I did one, but I didn't have time for the other one. So here I used matplotlib and the Seaborn library. And then I use Seaborn to generate a density plot again. You can see it looks almost the same as the one that we made with R, just a little bit different. I think there's some issues with the bandwidth here and here. So given sufficient amount of time, whether you're a Pythonista or an R person, you can get things to work. So we've generated the figures. We can also make a scatter plot of qual versus dp. And that gives us that same picture here. And then you can start playing with that to visualize different aspects or subregions of the plot. And the last part that I'll just run is even more advanced. So here we make a plot of basically the same data, but with the densities of both the qual and dp on the axes, separated by a number of constants. So you can get quite far from loading the data into running GITK to visualizing sort of all within one environment. And this is good, as the book points out, for debugging if something goes wrong, or if you want to run on moderate amount of data and just get a feel for how things work and then scale up. And the book also mentions here in this note in the epilogue that this is probably not the way that you want to do things, at least in visualization terms, if you have a lot of data, more than fits in memory. So this doesn't scale very well. And that leads then into exploring the Hail toolkit, which is scalable and specifically dedicated to that sort of processing. So with that, I will stop. I just had two more references that I wanted to share with you, and I'll post the link in the Slack channel. If you want to know more about notebooks and are notebooks a good fit for me or not, or what do I need to be aware of, there's a couple of very funny talks. There's one, I Don't Like Notebooks, by Joel Gruz. So this guy basically went to a conference about Jupyter notebooks and told them that he doesn't like Jupyter notebooks. That takes some guts, but he has some valid points. I don't think I agree with all of it, but it's thought-provoking at the least. And then there was a rebuttal by Jeremy Howard, who is a machine learning guru, and he has a talk, I Like Notebooks, where he sort of counters that a bit and talks about what, like basically, okay, what is known about notebooks and why they're no good or good. And you can sort of, balance things out and see where you stand on that end of the spectrum. And with that, I'll stop sharing and I'll hand the baton back to KT.
Yours, thank you so much. That was a very comprehensive and amazingly well-timed presentation. Thank you for walking us through that notebook. Really appreciate that. So we had some questions before we started the meeting. I'll put Adelaide on the spot. I know you had a question for the group. Geraldine's also with us. Thank you for joining, Geraldine. Great. We have time for a few, but Adelaide, I thought your question was very interesting, and I'd love to have the group talk about it.
Yeah, I want to go watch those videos that Joris just told us about what the pros and cons are. But I don't know, maybe Geraldine, you can speak to this. So we, switched up the GITK training while I was there to be in Jupyter notebooks. What are the advantages and disadvantages? Like, are people learning as well when you give the code to them, or how do we, that was so much information. It was so great, Joris. Thank you for your presentation, and thank you for putting that all in the book, because you get to see the bash, and the R. You know, you got to see all the different things cool things you can do with a Jupyter notebook. But when I sit down with people who are starting out, it's a challenge to decide which way to go. And I don't want to use Jupyter notebooks as a crutch, I guess is what I'm trying to say. So I don't know what, Geraldine, if you have any thoughts about that.
Sure. I mean, for the GITK workshops specifically, a big part of it was maximizing the useful amount of time that we could get out of the workshop, because we'd have, and these were pretty long workshops, right? They were 4-day workshops in many cases. And even so, with the amount of stuff we needed to cover, 4 days didn't feel like a long time. And so we needed to kind of optimize how we were going to deliver the training. And, we've had experience since 2012 is when I started. We've had experience trying different modes of delivery, including just showing up and being like, okay, here are the commands we're going to run, like copy what I'm doing on the computer. And that's too hard to follow. And depending, and people might have vision troubles and all sorts of stuff. It wasn't very helpful for everyone. It was still challenging for a lot of people. So we started giving, text documents with the commands so that people could type it. And so all of this was being done in the terminal, right? But you have still several layers of challenges, including for people who might not be familiar with the terminal already. That's a challenge. You have the challenge of setup, right? The environment setup. And actually, I should have started with that because that's kind of the biggest one, going chronologically in terms of the evolution of things. But I would say the environment setup across the years of workshop experience was consistently the thing that hampered us the most. You'd have people who showed up with Windows laptops, despite it being very clear in the workshop requirements that you had to have Linux machine or a Mac OS, and we didn't support Windows. Still should I think they were hoping we could do something for them. In many cases, couldn't really, so we pair them up with somebody else. And I understand, like, sometimes people don't have a choice of what machine they have, if their institution isn't supporting them, or that's just what they have. Anyway, so that was always a problem. And the problems around, familiarity and so on. And we ended up just spending so much time dealing with environment problems, helping people who weren't familiar with basic Unix commands, and just it took a lot of time away from learning the actual GITK stuff and focusing on the GITK stuff. And so in the context of like a short time training like that, where you have just very limited time, I would say the Jupyter notebooks really helps bridge that gap and just provide an environment that's all set and that's easier to navigate for most people, and where you can have all the instruction clearly there. You don't have to, you barely have to type anything, so you don't have to deal with problems of selection and things like that, which can slow some people down unfairly. And so I think it helps everyone be able, or maximum amount of people be able to focus on the actual scientific problems and tool problems, problems in terms of the interesting questions, right, and the concepts that you need to learn. The downside, obviously, is that in the sense that it is a crutch and band-aid for people not having the right environment or not having terminal skills and stuff like that, you haven't helped them on that front. And so they still need to go and learn that. And so in certain settings, if you have the ability to spend the time, I think it is in a way nicer to be able to run through like just command line. If you know that people are going to be working that way and they need those skills, if you can combine that training, I think that is like, it gives them, it sets them up in a way that when they walk away, they can actually do their work the way they're going to do it in their day-to-day. That's very powerful. GITK workshops, we just don't have that luxury. But I would say that's kind of the trade-offs when you're choosing how to do a training like this. It can be something where like you could do, if you have a multi-day thing, or like a longer kind of a longer cursus, start off with notebooks so that people can get on board and you know, get on board and tackle the interesting scientific questions before tackling learning Unix. In a way, is kind of nice because they don't really want to learn Unix in a lot of cases. They want to deal with the scientific questions. And so if you can kind of get them hooked and motivated and show them that early on in the training, they can already do cool stuff, then they'll be more willing to put in a little time later to learn the tooling that goes around. So that would be kind of my philosophy for that sort of thing.
Yeah, that's cool. I mean, I guess sometimes people have an expectation of what's possible to learn and beat me up, sorry, puke up. You know, to be able to learn the whole progression of what is needed, like from command line all the way through to executing a, you know, a Spark, you know, cluster to do Hail, and it's just not possible, and we all struggle with that. But you know, I'd love to hear other people's thoughts, or maybe we can continue the discussion in the Slack channel, because I'm currently being tasked with developing workshops, and the it's harder because it's not just the technical aspects of Unix command line. It's actually how to go in and on cloud, set up a VM, pull a Docker, have a notebook, you know, that stuff. That's why I like Terra, because it'd just be such a great shortcut to be like, let's go on Terra, and then it's all that behind the scenes stuff is done for you. But the expectations of the group I'm teaching to are a little bit different. So anything I can do to save time is great. But I think where I get stuck a lot of times is actually setting up the notebooks. I think that people want to know how to do it for themselves. And I'm just like, well, there's this thing called Terra, and you can go join it, and there's lots of notebooks on there. So
yeah, I think that the teaching methodology and so on is very dependent on the specific goals of the training and the specific goals of the group, and how people are going to be doing their work. Sometimes I find that, you know, I'm talking to folks who are interested in the cloud, and like, I don't need the Terra stuff. I just want to learn how to use the cloud. And then you kind of show them, and there's a lot, like managing the resources directly. That's a lot of work. And if you want to do it securely too, that's even a whole other layer. And then they realize how much it is, and then you show them, like, just for the record, this is what Terra looks like, and so on. And these managed services, and it's not just Terra, there are other managed services like that, right? I think people realize, wow, this does make it a lot easier. But I think it really depends very much on the group and their goals. To bring it back to notebooks, I would say the teaching aspect is really huge to me. I also like it as a way to distribute an analysis for reproducible science. Like if you're publishing a paper, and you can, instead of like vaguely describing things or giving links to the source in GitHub, and you've got some R scripts and stuff that maybe has comments. If you're lucky, there's comments that explain what things do in the R scripts. It's still pretty hard. Whereas if you just give a notebook, people can walk through, and you can annotate things. You can have illustrations. You can see the output right there. I think that's very powerful for reproducible science. And I think so beyond teaching, I think that's the other aspect that I find incredibly useful. And I encourage people, like, okay, you do your work in RStudio, that's great. We actually support RStudio in Terra now. You can use it, but think about, like, when you're publishing your paper, consider turning your R scripts and all the code that you ran, turning that into a notebook. I mean, keeping a notebook as you go is great for your own self, so that in 6 months you still remember how you did the thing, if you have to redo it or modify something. But also just for the publication stage, I think it has the potential to transform how we communicate science if you can really attach the code, the explanation of what was done in a way that's linear. And we all know that science is not actually linear. Like when we write a paper or we give a notebook, it's like a nice A to B to C to D kind of story of how things were done. That is a rewriting of history. That's not typically how we originally came to it. It just, you did a whole bunch of things, including some iterations, and then you realize the right way to do it. And you rewrite and you say, you do this and this and this and this, and you will get to the same thing. And you can demonstrate that. And I think the ability to present kind of a revised history that is linear and understandable for other people is really important. And I will get off my soapbox now. Otherwise I can hold you all for like hours. Sorry about that.
No, it's wonderful. And this is a great discussion. And as many have suggested, I'd love to continue it on Slack over the next week. It dovetails into chapter 14 about reproducibility, as you mentioned. So we'll cover that in some more detail. I think it's a wonderful idea again, for sharing and for reproducibility to use notebooks. So I'm looking forward to that. Just backing up from there, next week, Adelaide presents to us making Terra your own, or what I've called terraforming. So she'll be she'll be presenting next week. I also wanted to thank Joris for the wonderful presentation today. Very well organized, and yeah, it brings up some very interesting issues around how to teach and how to explain using this very powerful technology. I was blown away by it, to be honest. It was kind of the summit of the book because it allows you to put everything together in one place and very quickly get to an understanding of the data. So wonderful, wonderful meeting today. Well, we'll continue the discussion. Looking forward to next week. I want to thank everyone for joining. And thanks also to the folks on YouTube who are following along. That list of folks just continues to grow. So thank you for that. And looking forward to seeing everyone next week on the Genomics of the Cloud Book Club. Thanks for joining us today.